this talk, like what I will try to go over is how we use graph-based machine learning for healthcare services, like diagnosis prediction mostly in Oracle labs. So before I start the talk, this is a safe harbor statement that this is the information session mostly, and it's not in any products yet. So the agenda of this would be, we'll start with how exactly a graph model is beneficial about this classical relational model, and then I will go over the healthcare scenario and provide some background on what we are trying to solve and the exact problem definition that we'll solve, followed by our architecture that we designed, which we call KGRN. It's a combination of knowledge graphs with recurrent neural networks, and we show some validation on some publicly available data set, and then I will conclude the talk with some links that you can follow up online, and also the slides will be available online, so yeah, you can download it from here. So starting with the benefits of graph model. So what exactly is a graph? So just for overview, so you can represent your data in a graph model. So basically entities can be vertices, and relation between these entities are edges. So this is a sample example where you see there is a patient, and whenever this patient goes to some hospital, so there is an admission with that, connected to the patient. So apparently this patient had 3 admissions, and for every admission it can be connected with some diagnosis. There can be multiple diagnoses also for each patient, and once we have the diagnosis, those are also treated with some procedures and treatments, so we can have those. And this is an example of a heterogeneous graph. So there are the entities could be of different types. So here you see there is entity patient, there is entity admission, then diagnosis, then procedures, and treatment. So there could be different types of entities. And furthermore, each of these entities can have different properties. So even though like some of the properties are like ID, that could be value for the admissions, there could be different kinds of like lab results or like input fluids connected to each admission. So each of the entities can have multiple such features. So what are the benefits of graph model? It's more intuitive, so we can visualize the graph model and actually provide better explainability by doing like some multi-hop queries over this, and also we can aggregate information from heterogeneous data sources, as I will show. And lastly, also the data visualization aspect, and we can do this kind of like for multiple scenarios like cyber security or threat detection. It requires some investigation, and the graph along with this visualization techniques can enable this. So starting with this, like what kind of graph analytics engine we use? We use something we developed inside Oracle. We call it parallel graph analytics engine. So it's the in-memory graph analytics engine. We have both versions. One is shared memory version and the distributed version. And we have multiple research articles comparing this with some publicly available versions like Neo4j and GraphFence in Spark. We have multiple built-in algorithms in this PGX package, and also we also provide this graph query language, PGQL. So here is a sample example of PGQL, where it's very similar to there is a standardized graph query language similar to Scikit if you have used Neo4j. And for example, this is a sample PGQL query which shows like, okay, what are the other vertices which are connected to a vertex which has the features, and then the first name is Gerald and the last name is Hilbert. And this is available on Oracle Tech Network, so you can just directly go search PGX and go to this package and try it out. So now, how does this graph look in various domains? So in this talk, we'll focus on health science. So I gave an example of a health science, but it can be also used in other domains, as I mentioned earlier, like financial domains where you can have a customer can have multiple accounts, then accounts can have addresses, and in some cases you can have accounts trigger some alerts because they're doing some fraud transactions. So now that we know a brief about healthcare data, we will go in the background, what kind of problem we are trying to solve here. So like as I mentioned, so healthcare knowledge graph, like normally they incorporate information from different entities, And this kind of knowledge graph builds over time, like it's dynamic, so we can add more information. And the thing is, like, also what's challenging here is like you cannot take classical machine learning approaches and run it on top of this graph data. We have to build some customized graph machine learning algorithms that can work on this graph data. So now some more details about this healthcare knowledge graph. What we use in this specific problem is like we have some admissions. As I mentioned, admission is whenever a patient is admitted to a hospital, we have this log. And even though it's a node, it has a time series data connected with this admission. So admissions can be from a few hours to a few weeks. And during this time period, there are different types of events associated with this admission. Like it can be some lab events, it can be some fluids intake in the patient, fluids out of the patient, and some medications, prescriptions. All of these are inside this admission. And there are some pre-diagnosis information. So whenever a patient goes to the doctor, there is some pre-diagnosis connected with this admission. And based on that, we connect some external knowledge base also. So mostly the admissions are something that is already there in the healthcare, in the hospital database. And this kind of information, for example, this is diagnosis symptom information. This we can publicly extract from different knowledge bases. So there are some research articles also on this kind of extraction of this kind of relations. And what we do here is like we merge both of these in this knowledge graph, and we build a more enriched knowledge graph over which we will run our graph machine learning algorithms. So also, like, this is a sample example of how we can do in other domains. For example, retail. In retail, you have clients, they purchase some products belongs to some categories, and there are clients following categories. So this is a sample example of how this kind of knowledge graph also applies to domains outside healthcare. So in this talk, we'll focus mostly on the healthcare knowledge graph. So the features of the healthcare knowledge graph, as I mentioned, there are more unseen disease symptoms relations that are discovered over time. You can always update this knowledge graph with this. There are always more admissions coming by, so the underlying graph analytics engine should be able to support these updates in this knowledge graph. And there are the dynamic properties as well. So admissions can vary over long duration, so from a few hours to a few weeks. And it goes to different medications, lab tests. And also, as I mentioned, so this kind of, how do we construct this kind of KGs? We construct based on some internal information which is there in the hospital databases, and some publicly connected information like disease symptoms. And so now we know a brief about how the healthcare data set looks like. We go into the learning objective here. So we have an admission. So this is exactly how the admission timeline looks like. So this is admission for one single patient. And this has some duration. This is, I think, around 100 hours. And in this case, with the start of the admission, there are 4 types of events associated with this admission. So there are drugs, there are fluid out of the patient, fluid into the patient, and lab tests. And there are some examples of each type of the events. For lab tests, there are like platelet count. For fluids, there are insulin over time, then fluids out of the patient, and then there are drugs prescribed. And our objective here is, like, given this kind of admission, we want to predict what would be the diagnosis connected to this admission. And it's challenging because most of the current systems, what they do is, like, at the end of the admission, there is admission discharge. And there is a discharge summary connected to this admission. So there are, like, the systems like Amazon AWS, you upload this admission discharge, and then it will try to predict the diagnosis for you. There is a drawback here, like these systems can help only at the end of the admission. You cannot get the summary discharge in an ongoing admission. So, and also there are some other trivial challenges which are like you have to do some data normalization because there are 1 points and there are continuous events. So with these things now we try to go into how we can solve this learning objective. So here comes the KGRN. So the first thing is, like, we basically model this as a sequence problem, which is trivial because we have, like, admissions, this goes over time. So there are, like, some lab results which go after one after other. There are events of this. And so we, like, to feed into RNNs, there is, like, you need some normalization. And this kind of normalization is, like, you can break up into chunks of equal time events. And for each of the chunks, if there are continuous events, you can break those into some equal number of one-point events. So these are some classical data normalization techniques that are used for feeding some this kind of data to recurrent neural networks. Now, once we have that, so just a brief introduction of recurrent neural networks. So what kind of problems is used for? As I mentioned, so it's used for this kind of sequence prediction problems. So it's used in stock market prediction, also for machine translation. Machine translation, like in case of you have some French text, you want to translate it to some German text. And what it does is like it gives the state of the input, and it basically takes the sequence of input and tries to predict the sequence of the output. So this can be a French sentence, this can be a German sentence. So we use this kind of recurrent neural network for solving this diagnosis prediction problem. And as I mentioned, so what we do is like we do some data normalization techniques here, like we convert the continuous events to this one-point events, and also we do some because to feed it to RNN, basically we need some fixed number of events per chunk. So we also sample some events from each of the chunks so that we have some equal number of events. And then this is simple for then this is classical how you feed this to a recurrent neural network. And so this is basically the brief overview of the architecture. What we do is like we have this kind of 4 types of events that are there. We have aggregators for each kind of events. Aggregators are normally like you can aggregate information per type of event. You can use max pooling, min pooling, all of this kind of aggregators. And once you have that, you can feed this aggregated embedding to the recurrent neural network to predict the admission encoding, which is basically encoded in like a fully connected neural network, predicting the diagnosis. So this is basically the structure of the recurrent neural network that we're using for the admission, encoding, generation. And this is still, we did not use any part of the knowledge graph here. We're just using the information from the admissions point of view. So with this as a baseline, now we look into how we can incorporate the information from this knowledge graph. So as I mentioned, so we collect these admissions based on this external information that we collected from publicly available sources. And so what we want to do here is like, given we are trying to predict the diagnosis for this admission, what external information can we get from this knowledge graph to enrich our diagnosis prediction? So what we do is like we try to get the nearest neighbors for every admission in that knowledge graph. And here we also use some internal implementations inside our PGX engine. And so here like we use the weighted personalized page rank. And for the weights we use like for the disease symptom connections, we find out there is an importance of a symptom for a given disease, and we use this as a weight. For admission symptom disease, so for each admission, as I mentioned, there is a pre-diagnosis information that is connected whenever the patient comes to the doctor. And we use a kind of a fuzzy similarity matching to give the weight to this admission symptom connections. And given this, we run this weighted page rank algorithm to find the top admissions for each given admission. So for example, here we have the input admission 1, and what are the other top similar admissions? So here we put a threshold so that we don't take admissions which have very low similarity. So here we get like there are 2 admissions which cross the threshold, and what we take now is the features of this admission. And this we feed along with admission encoding that we generated earlier in the baseline. So this is the state that we had. So earlier we were doing the encoding for the input admission, and this we consider as our baseline without incorporating the information that we aggregated in the knowledge graph. And then what we did is like we aggregate some information. It could be some static information like the diagnosis information of the neighbors that we got. And then we kind of concatenated this information with the admission encoding and fed it to another predictor. And this is predicting the diagnosis for our case. So here was the admission encoded that we had in the beginning, which used the recurrent neural network here and here we are using the static features of the neighboring diagnosis, and this is fed to the prediction model. And here is this prediction model is just doing a multi-level classification task. So this is basically the kind of overview architecture of the KGRNN. And now for some empirical validation, how good this works in practice. So we took this Mimic3 dataset, which is a relation database from the Beth Medical Center, and this has information of around like 46,000 patients and around 58,000 admissions and few millions of events in total. And what we are trying to do, this is like, as I mentioned, the final task is a multi-level, multi-class classification. What it means is like every admission can have multiple diagnoses, and there can be more than one possible diagnosis in total. That's the multi-level, multi-class classification, and we focus on top 50 most frequent diagnoses in our database. With this, we compare how much information does the additional knowledge graph bring over the baseline, and so we see there is some improvement, and then we wanted to see, okay, we get some improvement, can we explain those improvements also? So here we try to get, for example, the top one shows our input admission, and this one is the most similar neighbor. So here we have the predictions of the two predictions. One is the baseline prediction, which is shown in yellow, and other is the value prediction, which is the predictions of the KGI model. What you see here is like for the baseline, none of those cross the threshold. Like, because it's a multi-class classification problem, we put the threshold at 0.5, so any probability of more than 0.5 is taken as a positive hit. And for the baseline architecture, we see there is no prediction here. However, when we have neighbor information, we see that, okay, it helped to push the boundary, so we have now a positive hit. But it's interesting, like also for cases which there are some neighbors, but they don't actually enable the baseline to cross over the 0.5. So it helps only if there is some positive hit in the admission and the neighboring admission that is extracted from the KGI. So this is one of the expression. Another thing that I mentioned at the beginning, we don't want to predict at the end of the admission. So what it says, like here we have one single admission, and these are the 4 types of events. So they're like these two actually are single events, it's just two medical care providers. So what it says, like there are 4 types of events basically, and this is one single admission, and this is the whole duration of the admission. And throughout the duration of the admission, we should be able to predict what is the probability of some diagnosis. So here for visualization purpose, we just show six diagnoses among the 50, and these are like 3 positives and 3 negatives. And we show that, okay, we can actually predict the probability of the diagnosis as the events are coming in. Normally for the, when you're predicting with the discharge summary, then you actually just take the information here, and then you cannot do any prediction at this stage, because the importance here is if you have the probability of the diagnosis at some point here, you can improve your treatments based on this. Here we don't see any any such thing, because this is a static data set. So here we cannot actually influence the treatments based on whatever we are predicting. But in practice, you can actually improve your treatment that you are giving, because the model is saying that you have a high probability that you will be diagnosed with this. So you can improve your treatments even before the end of the admission. So that's for the empirical evaluation. And then now I will just conclude with summarizing the details. So what we are doing here is like we actually presented a novel approach that we are doing with combining knowledge graphs with GraphML, and this is just this is just one of the applications that we are doing for GraphML. We also tried it in different other domains, like for example retail. In retail, you can build up recommender systems. In recommender systems, the graph is like a IP, like a user and item graph, and then you can predict basically what is the connections between like users and items, and you can it's a link prediction problem. Then you can recommend products to items. You can recommend items to users. And then in finance, for example, this I already showed with the example. You have a user account and transactions graph. And then in cybersecurity, you have an IT domain graph. There, this kind of approach could be used for bot detection. And so we also have blog articles about this in more details of how we use knowledge graphs in healthcare, and also this exact technique that I mentioned with more details in the architecture. Because what I presented here is a high overview, because for aggregators, for example, we use multiple types of aggregators for each type of feature and before feeding it to the RNN. And the tools that we use is are developed at Oracle. So we are using the PGX, which is a parallel graph analytics engine, as I mentioned. You can download this from this link and try it out. Also, we have the PGQL language, which also you can download and try out. And finally, we have some online samples available in the GitHub repository. So you can just clone it, and yeah, it's just clone and download and run. So that's the summary. Yeah. So.
Thank you very much.